This is the second part on neural network. Last week, I gave you an intuition of what neural network is. And today, I want to build a product with you. We'll build an image classifier. So just to review what we already talked about in the last lecture, neural network is essentially when you stack up and chain together a whole bunch of simple models. Think linear regression or logistic regression. And when you stack them up and chain them together, you end up with this powerful model that we like to call neural network. And I give you an intuition for what I mean by stacking up and chaining together simple operations by looking at the example of cooking, where I have 3 ingredients. You could have a blender that takes different amounts of each, different weights, and make something new. And here the blender represents a simple operation. It gets interesting when you add a second blender. And each of these blenders have their own set of weights, how much they will pick from any of the input. Here, for example, the first blender takes a lot of egg, whereas the second blender takes a lot of broccoli. And then you will have a third blender to take the outputs of these two and then blend them into a single output. In the world of neural network, this would be a neural net with 3 nodes, where each node, or each neuron, I should say, represents one simple operation, and it has one hidden layer, which is this, and there's an input layer, an output layer. And the whole purpose of training the model is to find the best set of weights, or these lines, how much of each input goes to or each output goes into the next input. Those are the learnable parameters. Let's go back to the old familiar example of predicting house prices. And this is a picture we're all familiar with. You have this data set of houses, each row being a house. Each house have a bunch of attributes that we like to call features, and the price. And the price is a label, or the output that we like to be able to predict. You have this learning algorithm, which is gradient descent. And with that, you will build this model. And once you have that model trained, now you can feed into it a bunch of features like the wealth area in bedrooms, and it will predict the house price. Now, we solved this before using linear regression. So let's start there. Here you see this linear regression, but with different visual. There's nothing new in terms of how we built a model, but just a different visualization. So the model itself, the linear regression, is W0 plus W1, X1 all the way to X4. X1 through X4 are the inputs, are those features, the columns that I showed you, area, bedroom, crime rate, and maybe the household income. And well, you plug them into this equation and you get a prediction of the price, and that could be the end of it. And if you think about what these W's really represent, they signify how much each of these inputs contribute to the prediction. So W1 times X1 plus W2 times X2, right? And again, remember that during training, we were tuning or tweaking these W values that would best fit our training data set. Now, this turns out is in fact a neural net already, but it has only one neuron. This is the neuron, and it represents one simple operation, and that operation is linear regression. Now, given the intuition that you already got from that Blender situation, you may guess what I'm about to do next, which is grab another linear regression with its own set of weights and make some predictions here, and then have a third one that takes the output of these two as input along with its own set of weights. So at high level, I may be looking at something like this. Again, W0 to W4 are the parameters for this operation, for this neuron, and then 5 through 9 for this one, and then 10, 11, and 12. So in total, we'll have 13 trainable parameters. And that's pretty much already a decent neural net. There are some details that I left out, like the activation function and such, but that is not critical for you to get started with. Now, if you look at this image, it has 3 neurons, it has 1 hidden layer, 1 output layer, and 1 input layer. And this could already be quite powerful in capturing patterns that we as humans may not be even able to do that. For example, maybe what this neuron is picking up or outputting is a measure of how many people can live in that house. Because as you can see, the thickness of the arrows suggests that weights or W's are large for area and bedrooms. And similarly, the second neuron might represent the school rating. And then the house price is predicted based on a combination of school rating and a number of people who can live in the house. Now, I was able to come up with this story to tell you what these hidden layers are representing. But imagine if you had hundreds of input features and a whole bunch of hidden layers. It would become impossible for us to get an idea of these underlying patterns. And that's really the beauty of neural net. You don't need to know what the patterns are or how to come up with patterns. You just come up with the architecture, step back, let the training job figure out all the model parameters. And by the way, one other terminology I want to clarify here in neural network is weights. Up until now, I talked about model parameters, and now I started calling them weights. They are the same thing. W's are weights or parameters. Same thing, identical. All right, so that was our first neural net. And we also talked about the idea of a deep versus wide neural net. That in real life, you probably have a whole bunch of layers. And if you have many layers, we call it a deep neural net, right? So that's what we talked about in the last lecture. And now I want to build something with you and walk through the code. And here's what I'm going to build. Already built, rather. All right, let me... So I have this image classification app where I can handwrite a digit, and then it will predict that this is a number 1 with 98% probability. And let me see. And for a 0, it make a correct prediction with 98% the probability too. So this is what we're going to build. But let me motivate you on why we would build something like this. It turns out the closest use case for this I could find was in Google Doc itself, where if I go to insert a special character, you can, well, you don't have to look for all the characters to find the one you were looking for. You can just draw it like this, and it predicts that what you were looking for is a sigma. Or in our case, if I put 0, it can tell that you're looking for number 0. Right? So that is one. But this idea of extracting text out of image has a lot of applications. And that's what I'm going to show you next. Here on top left, you have this check deposit on mobile, where I presume when you take an image, there is a machine learning application that extracts these texts out of the image. Or on the lower right side, imagine this police car is constantly taking images of the plates of the vehicles that are passing by, and then a machine learning application like ours will extract the plate number. Maybe it can feed it into a query, a database, and figure out if that vehicle needs to be stopped for whatever reason. Kind of like a automated monitoring. So these are some applications of this. But let's go build it. The first step is at high level. What we need is just like any other ML project that I talked about so far. You're going to need training data. These are images of zeros and ones with their labels. So this one has a label 0, label 1. We need thousands of these to feed into our learning algorithm, which is gradient descent, and build a neural net or train a neural net with it. And once you have that neural net trained, you can give it an image and it will predict the true label of it. And that's essentially what we did in that demo. It's just that instead of feeding it an image directly, I created an image by handwriting on a canvas. But I could have just fed it an image directly. All right, so where do we get these training data from? There are a bunch of data sets that are publicly available that have been heavily utilized in the machine learning community for purposes like this, for educational purposes, for looking at algorithms, for experimentation. One of those data sets is called MNIST. This is a set of 70,000 images of handwritten digits. So 1, 2, 3, from 0 all the way to 9. And here you can see a whole bunch of them. And each image comes with a label, so you can tell what that image is for and use it for image classification or for generative image generation, anything. And that's what we're going to do. Because we are only interested in 0 and 1, we will discard all the other images except for zeros and ones. So that's our data set. And before I show you the code, there is one other piece that I want to talk about, and that is, up until now in our discussions, we added data, we use it to train the model. We're going to do pretty much the same thing with one tweak, which is I'm not going to use all the images that I have to build the model. I like to set aside a small portion of it, like 20% of my images, for testing. So I will build my model on 80% of data. And next, I'd like to know how good my model is, how accurate it is. Then I will use that holdout set, the test set, to see how the model performs on that. And the reason I do this is you don't want to use the same data that you use for training to test the model, because then your evaluation of how good the model actually is could be biased. Maybe your model just memorized the training data, and because you're feeding it the training data for evaluating it, it may falsely give you the impression that your model is better than it actually is. All right, so that's what we're going to do. And here's the code. I've defined a function called getDataset. It's up here. I'm not going to show you that. it essentially grabs this data set, MNIST data set, download it, get rid of everything except for zeros and ones, and then split it into a train and a test subset. But what comes out of it are these 4 data sets, right? So the train suffix means that we're going to use that data for training it. The test means you're going to set it aside for later. I have 11,800 images for my training and 2,900 for testing. And here are some examples of these images and their labels. Right? Next, so this was the data acquisition piece. If I go back to this image, so I talked about this piece, the images. Now I'm going to talk about this part where you feed an image to a model. That could be here and here. At the first glance, it may not make sense to feed an image into a model, because we talked about these models being mathematical expressions. So how can you feed as input an image, or in the case of language models, text or audio or anything like that, into a math expression? Well, it can't. It has to be numbers. These math expressions only can take in numbers and do operations on numbers. And it turns out, in fact, images are numbers. The way they're rendered on the computer screen is such that we perceive them as images, whereas underneath they're just numbers. And to illustrate that, here I have one of the images. So here's one of the images. There's an image of a number 1. I have rendered it quite differently for you to see what is the true representation of these images beyond our visual perception of it as being a black and white image. So the image is essentially a 2D array of 28 by 28 size. So each box here, or each number, represents 1 pixel. So this is the size of this image is 28 by 28 pixels, if you like 700 something. The number that they hold signifies the light intensity in that pixel. So 0 means it's total dark. 255 means the highest brightness, and anything in the range of 250 means very bright. The shady gray areas are like in the range of like 150, 128, so on and so forth, right? So this is what we have. We actually have this 2D array of numbers that we want to feed into that model. And for that, the first thing I want to do is to take it, turn it from a 2D to a 1D array. It's called flattening it. So here's what I mean. So I have 8 by 8 visuals for an image, but imagine it's actually 28 by 28. What I do is that I flatten this, make it a 1D, and that becomes 784 length of a one-dimensional array. And that feeds into the input layer of neural net. So this is in fact our neural network. It has an input layer with 784 or 28 times 28 elements. And then I have a hidden layer of 100 neurons, and I have an output layer of 1 neuron. The reason I have a single layer on the output here is because all I need is just a number between 0 and 1, and that would represent the probability that the image is 1. So if the probability is less than 0.5, I can say the image is 0. If it's more than 0.5, I would say it's a 1. And in that UI that I showed you, I'm going to go back to where it says confidence 97%. It's actually the output of the of this neural net, or the value that comes out of the output layer, the number between 0 and 1. So this is a neural net. And by the way, you don't see any lines connecting these, but that's just because it was too much work to draw all these lines. But you might imagine all these neurons from one layer are connected to the one in the next layer. All right, with that, let's continue with the code. I got my data set and I presented to you the visuals of what these images actually are. The one little step in data processing I wanted to do was, it turns out neural nets are not very good at tackling large numbers like 200 something. It's much better if you can transform them into a range close to 0. And that's what the scaler is doing. It takes these images and shifting them such that the mean of all these numbers is around 0, and then scaling them such that the standard deviation is around 1. Nevertheless, there is not much else going on. I just take my input, transform it a little bit before I feed it into my neural net, and I call it scaled. But here's the model. It's just 1 or 3 lines of code, whatever. What I'm doing here is I import this from sklearn. All right, so that's my model, and then hidden layer sizes. What I'm saying here is that it's just one number, which means one hidden layer, and it has 100 neurons in it. If I wanted to have 2 layers, each 150, 120, I would just say 50 and 20, right? And here I'm saying that during my training process, if you remember, it's an iterative process. I'm saying do no more than 5 iterations. And this is where I train the model. I hope you notice that because I'm using sklearn, the API is identical with what we did before for logistic regression or linear regression, which is you define your model, and then you apply the fit method, and it will train the model on this x's and these y's. And it took a fraction of a second, and you see the loss drop dramatically in the 5 iterations. And now you have a trained model. So we can go and use the model. Before that, let me show you what the model has in it. Here are the number of trainable parameters in the model, 78,601. These are the number of weights or model parameters that needs to be tweaked during training. And in case you're wondering how we ended up with 78,000 parameters, here's an intuition for that. So you have 784. Each of them have a line connecting to each of these 100, right? And that line represents that parameter that need to be tweaked. So that's 784 times 100. That's already 78,400. And then there are some additional ones from here to here, and you have the bias term or the intercept as well, and that all adds up to 78,601. But that's our model. It's been trained with 78,000 learner parameters, and here where I can make predictions. At this point, I can take the model, apply the predict method, and give it an image. And then I'm like, for the first 10 images in that test data set that I haven't looked at yet, right? Show me the true label along with the image and my prediction of the label. And here you can see it. So this is the image that was fed. This is the first image in the test data set. It was a 0, and we predicted to be 0. And in fact, all of these have correct predictions. And next, well, not all, well, everything here in these 10 images are correct prediction, but here are the images where the model didn't predict correctly. So this was in fact a 0, the model predicted to be 1. And we had only 4, that's why the rest of images remain empty, because we didn't have enough incorrect predictions. And here's the important number, model accuracy. Accuracy is the percentage of predictions that were made correctly. So if an image was 0, we correctly predicted it to be 0. And if it was 1, we correctly predicted it to be 1. So we are accurate 99.8% of time. And in fact, it looks like we were incorrect only in these 4 cases, right? So we have a model, we trained it, we made some predictions with it, and now we have some measure of accuracy. And this piece of code, by the way, this is the last piece of code. This is where I use that user interface, this UI here, right here, to render some experiments. So this, you don't have to have this, but it's nice to have it for examples like this where you can actually interact with your model. And feel free to play with it. There is this Gradio library that is used in Python community for this type of like user interfaces. And what I'm doing here is that it has a sketchpad, and we use it as an input. When the user draws something and hit submit, it invokes the predict method on the model. So you're running model.predict on that image that you just drew, and then it prints the it prints the prediction and the probability. So essentially it takes the model output, which is the probability, and then if it says if it's more than 0.5, it takes it as 1, and otherwise it takes it as 0. So we used scikit-learn library for the example that I showed you, but that was primarily because that was the library that we were already familiar with, and it provides a very simple interface or API. But if you're interested in deep learning and building neural net, currently the most popular library, the open source library, is PyTorch. This was created by Facebook and is probably the one that's most popular right now. If you go a few years back, TensorFlow, provided by Google, was also very popular, but that's no longer the case. But if you find older tutorials on YouTube and elsewhere on deep learning, chances are they used TensorFlow just because at the time it was a very popular library. And like I said, scikit-learn, I used it just for educational purposes. Maybe you can build some very simple models with it, but generally speaking, it's not what you would use for building neural net. All right, I hope that was useful.